In this video, we are going to talk about acid-base titrations. Now, in an acid-base titration, the concentration of an acid and in that fact, it could be a base, is determined by neutralizing the acid or base with a solution of base or acid if you are trying to titrate with a base of known concentration. So essentially what you're doing is you have an acid, you don't know the concentration, so you get a base and you know the concentration of it and you titrate it. And you add a small amount of the base until you get to what is known as the equivalence point. Now, the equivalence point is where the reaction is complete. And so this occurs when the number of moles of hydroxide is equivalent to the number of moles of hydronium ion. So if you have a 1-to-1 mole ratio between your acid and base, then what that means is the moles of your base are going to be equal to the moles of your hydronium ion. So a lot of times with this definition of the equivalence point, you'll see it as the number of moles of hydroxide are equal to the number of moles of hydronium ion. And that's only true when it is a 1-to-1 mole ratio. So another way you can look at this is the number of moles of the hydroxide that is added by the titration equals the number of moles of the hydronium ion that is present in that acid solution. Now, the end point is the point in the titration when the indicator, so this occurs when the indicator changes color. Now, an indicator, we call these acid-base indicators. And an acid-base indicator is a weak organic acid whose color is different than its conjugate base. So what that means is you will see a color change when you change from it being an acid to the conjugate base. And when that color changes, that is the equivalence point. Now, you need to make sure that you can have an indicator that has a strong color change so that you only use a small amount and the presence of that weak organic acid doesn't influence the acid-base chemistry that's going on. And the color change of an indicator is going to change over a very specific and narrow pH range. And that range is usually about 2 pH points. Now, when you are choosing the indicator, you need to select an indicator that has a color change at a pH that is close to the pH at the equivalence point of your titration. So there are all different kinds of indicators, and we know the pH of where the color change occurs. So you have to pick an indicator that will make sense with the titration that you are doing. All right, so let's look at the titration curve for a strong acid strong base titration. Now, remember, both strong acids and strong bases dissociate completely in water. That is the definition of a strong acid and a strong base. So there is no equilibrium. Now, a strong acid and a strong base titration curve is going to look very pretty. So you're going to have your curve, and it will start out at an initial pH, which will be acidic. On your y-axis, you're going to have pH, and on your x-axis, you're going to have the volume of the titrant. Most of the time, it's going to be a base. But we'll see later on where you can have volume of acid on your x-axis. Now, you're going to start out at a low pH, and as you add base, it's going to rise up until it shoots straight up, and then it will level off. So there's kind of 4 parts to this titration curve. Here we have our initial pH. So that is going to be before you add any base. Now, as we move along this area here, this is before the equivalence point. So this is before we've reached the equivalence point, and we should have more acid than base in solution. Now, as you keep going up at the steepest point, the highest point of the curve, usually right here in the middle of this straight line, you want to find the steepest slope. This is going to be your equivalence point. This is going to be your equivalence point. For a strong acid and strong base, the equivalence point is going to have a pH of 7 because the salt that is left over is from a strong acid and a strong base, and it's going to be a neutral salt. And then after that, you're going to get an area on the curve where we are beyond the equivalence point. and this is going to have a pH that will be greater than 7. When you are before the equivalence point, you should have a pH that is less than 7. So at the equivalence point, the pH rises very rapidly, and that is because you are at that time in the reaction where you have equal parts acid and base. So phenolphthalein is the indicator that is used most often with a strong acid and strong base, and it has a pH change. We'll say the equivalence point here is 7. Phenolphthalein has a pH change or a color change at the pH of around 9. It's really in between 8 and 9. And so here, if you notice, the difference in the volume right here is almost 0. So that's why we can use phenolphthalein. It's a good indicator because the change in color is going to be very close to that pH at the equivalence point. All right, let's look at how we can calculate the pH for at these different places for a strong acid, strong base titration. So let's look at an example. So we have 40 milliliters of a 0.1 molar HCl solution is titrated with a 0.1 molar sodium hydroxide solution. So let's calculate the initial pH the pH after 40, or let's do 20 first. Milliliters of sodium hydroxide is added, and 50 milliliters of sodium hydroxide. So essentially what this is going to look like is we're going to calculate it at 0 milliliters of sodium hydroxide, 20 milliliters of sodium hydroxide, and 50 milliliters of sodium hydroxide. So let's start off with our initial pH. So we have 0 milliliters of sodium hydroxide. So at this point, we only have our strong acid in solution. And remember, when you're dealing with a strong acid, the concentration of the hydronium ion, which is what we need in order to calculate the pH, is equal to the concentration of your strong acid. So if we look at our problem, we had 40 milliliters of a 0.1 molar HCl solution. So the concentration of our HCl is going to be equal to the concentration of our hydronium ion, which is 0.100 molar. So the pH, we just have to negative log it. And that is going to give me a pH of 1. All right, let's look at the second part of this. It is going to be at 20 milliliters of sodium hydroxide. So I need to calculate the millimoles of acid and base present. So I have 40 milliliters of my acid. That's what I get from right here. And I have 0.1 molar HCl. And I notice that I also have 0.1 molar sodium hydroxide. So 40 milliliters of my acid times 0.1 molar of my base is going to be equal to 4 millimoles of my acid. Now I can do the exact same thing for my base. And that is going to give me 2 millimoles of my base. Now here I can see that I have more acid than base. So the concentration of my acid is going to be greater than the concentration of my base. But realize it's not going to be equal to what it was before. So I have to look at my neutralization reaction. So I'm going to have the reaction between HCl and sodium hydroxide, which will yield water and sodium chloride, which I know sodium chloride is a neutral salt. I start off with 4 millimoles of my acid, 2 millimoles of my base. My base is going to be completely consumed, and that gives me 2 millimoles of my acid left over. Now I can divide that by my total volume, which is going to be 60 milliliters. Notice that my millis cancel out, and I will be left with units of molarity. And this gives me a molarity of 0.0333. And keep in mind, since this is the concentration of my acid, this is also the concentration of my hydronium ion. So I can get the pH by just simply getting the negative log of the concentration of my hydronium ion. And I get a pH of 1.48. Now, does this pH make sense? When we had our initial pH, we started off as a pH of 1. Now, in part 2, I added base. So if I'm adding base, I should see an increase in pH, and I did because it went up to 1.48. Now, I'm going to actually add another part to this. So I'm going to say part C is going to be 40 milliliters. And then D is going to be 50. And you will see why in just a second. So if we do part B, we see that the pH goes up. Let's look at part C, which is 40 milliliters of sodium hydroxide. So again, I want to see where I am on the titration curve. I want to see how much acid and how much base I have in solution. So I didn't change the amount of acid that I have. I didn't add any. I didn't take any away. And so I have 4 millimoles of my HCl still present. Now I can calculate how many millimoles of my base I have. So I can take the volume of the base that it's added, multiply it by the concentration, and I notice that also gives me 4 millimoles of sodium hydroxide. Now, at this point, the concentration of my acid is equal to the concentration of my base. So that tells me I am at the equivalence point. Now, what is the pH of a strong acid, strong base at the equivalence point? I know the pH has to be equal to 7. So I don't have to do any calculations here. we are only going to have, we're going to completely consume the acid, we're going to completely consume the base, so we won't have any more acid or base in solution, which means that it is a pH of 7. Now, finally, let's look at the 50 milliliters of sodium hydroxide. Now, since 40 milliliters of sodium hydroxide, I was at the equivalence point. If I add more base, I should be beyond the equivalence point. So my base should be greater than my acid. So let's check to see if that is true. So I still have 4 millimoles of my acid, and now I have 50 milliliters of sodium hydroxide. I can multiply that by the concentration, and that gives me 5 millimoles of my sodium hydroxide. And I can see here I have more acid than base, so I am beyond the equivalence point. So I can put together my neutralization reaction between hydrochloric acid and sodium hydroxide to yield water and my neutral salt. And I have 4 millimoles of acid, 5 millimoles of my base. So my acid is going to be my limiting reactant, and I'll have 1 millimole of base left over. Now, to calculate the pH, I can use the concentration of my base. So I have the concentration of hydroxide. Remember, sodium is a spectator ion. It's not participating in the chemistry, so we don't really care about it. And this is going to be 1 millimole divided by the total volume, which is going to be 90 milliliters. And I get that 90 milliliters because we add the 50 milliliters that we had from the sodium hydroxide and the 40 milliliters that we started off with our acid. And that gives me a concentration of hydroxide equal to 0.0111 molar. Now I can calculate the pH by getting the negative log of that. So when I calculate the pOH of this, I get 1.95. Now, if you stopped here and said this is the pH, it would not make sense because we're beyond the equivalence point. We should have a basic pH. So remember, if you calculate the pH, you need to plug that into the equation. pH plus pOH is equal to 14. So to calculate the pH, we would take 14 minus the pOH. So down here, my pH is going to be equal to 14 minus 1.95, which gives us 12.05. And that pH does make sense because it is a basic pH.